Hello, my name is Adamatzky. I'm professor of international computing at the University of the West of England, Bristol. Today, I will give you a talk about functional fungal materials. As we know, CO2 emission from building sector is highest in 2019, which put our ecological system at risk. A solution could be in building self-growing, organic, recyclable, eco-friendly buildings. In the post-apocalyptic world, we will grow houses from fungi. That was original idea at the beginning of our Fungal architecture project, funded by European Commission. The project team includes myself, UWE Bristol, Phil Harris, Chita, Denmark, Han Boston, Utrecht University, and colleagues from a mobile company in Italy. The idea was to use hemp substrates, colonize them with fungi, and produce building materials from them. But here you can see examples of the colonized substrates. Here, example of the building built from fungal bricks. Hemp bricks colonized by Mycelium, not by us, but by some other colleagues in the States. So, typically, houses are built from Mycelium-bound composites. The Mycelium-bound composites are dry. Mycelium is dead. It doesn't feel, it doesn't respond to information. However, if we leave some windows with living mycelium, then we can use this mycelium, which is shown by red on the picture, to sense information, to transmit information, to make decision making, and to implement computation. And in my present talk, I will be introducing to you these materials. Fungal sensors and computers. How it started? 4 years ago, after completing my experience with slime mold, I decided to check if fungi can show the same electrical oscillations or periodical changes in electrical potential as slime mold does. So I insert electrodes in fruit bodies, as shown in this picture, recording electrode inserted in cap and ground electrode in the stem, and recorded differential potential for days and days. I found that fungi exhibit action-like potentials. They have visible depolarization, repolarization, and refractory period. On this picture, you can see typical setup. Piccolo DC converter, analog to digital, grow tent, where fungal substrates are kept, and fungal substrate in the plastic container, and pairs of differential electrodes inserted in the substrate. More or less picture. So what we observed? We observed that fungal substrates demonstrate large varieties of spiking, as you can see on the spot. Typical spikes are enlarged in the insert. Trail spikes can be 2 hours, as shown on the spot, but it can be also 10 hours or even 20 hours. So fungal substrates, during their lifetime, they switch from between high frequency and low frequency oscillations. When we insert electrodes in the substrate and change its resistance, we observe resistive spiking. As you can see on the spot, we see on the right, you can see a train of resistive spikes. And here are the enlarged trains of resistive spikes. So the resistance of the fungal substrate is changing over time, probably due to transportation of water. After observing endogenous spiking and reductive spiking, we saw that possibly we can map some external stimuli when we stimulate fungal substrates to the patterns of electrical activity. So we have done experiments with fungal skin, published in the paper referred here. Fungal skin is a mycelium grown on liquid culture. So basically it's a pure mycelium, several millimeters in height or thick, several meters thick, and it reminds skin, even when you look at it. So we insert electrodes in this fungal skin and subjected skin to stimulation. We applied weight and we applied light. On this spot, you can see moment when weight was applied as W star and moment when weight is removed by WO. When light is applied, we have L star, and when light is removed, LO. So what happens? When weight is applied, fungal skin responds to a large spike of potential, followed by a wave packet of smaller spikes, high frequency spikes. And then nothing happens. When wave is removed, we have the same repetition. Large amplitude spike and wave packet of several spikes. When light is applied, as you can see on the spot, potential starts to grow and it grows until light is switched off. Then potential drops. So fungal substrates can discriminate between types of stimuli. They respond differently on-off to loading and respond continuously to light stimulation, as you can see on this plot. We return back to buildings, but when we experimented with this fungal skin, we thought, okay, what if we will have inserts of living fungal skin in fungal vermels? To test how it all works, we made a hemp pod colonized by oyster fungi, insert electrodes, and attached the pod to a t-shirt, as you can see on this photo. Then t-shirt was subjected to mechanical and chemical stimulation. At first, we applied malt extract, which is basically food for fungi, therefore fungi like it. To the application of the malt extract, fungi responded with high frequency oscillations because they like it. To stretching, fungi responded with changes, long-term changes of the electrical potential. But again, it was one-off response. Fungal response to loading. To check fungal response to loading, we prepared fungal box. Paper is referred at the bottom of the slide. And insert electrodes at the size of the block. Then we apply different weights, 8 kilo, 16 kilo, 32 kilo. 32 kilo was crushing fungal blocks, therefore we stopped with 16. We found that indeed fungal blocks responds excellently by changing patterns of the electrical activity to application of the weight. On the spot, you can see example when weight is applied on and the weight is removed off. So basically by classification of the distance between spikes and length of train of spikes and amplitudes, we can separate between weights which have been applied to the fungal block, between 8 kilo and 16 kilo. What is more cool is that fungal blocks exhibit habituation, as all living creatures do. So the more often you apply weight, the less will be reaction. Our brain is the same. Can we do computation with spiking fungi? Yes, indeed. At first, we demonstrated this with a single fungal colony. We took scan of the colony with our colleagues from UWE University. We inserted a matrix of simulated electrodes. You see colony on the left and matrix of the electrodes inserted on the right. Then we simulate propagation of electrical activity on the colony using Fitzhugh-Nagumo equation. On the plot, you can see several snapshots of the propagating activity. Then we assign 2 electrodes as input electrodes, and all other electrodes were recording output electrodes. And we simulated colony with binary strings of 2 bits. String 01 means nothing on one electrode and impulse on another. 10 reverse and 11 when impulses are on 2 electrodes. Then we recorded on all output electrodes coincidences of spikes, as you can see on the plot. And from these coincidences, we derived logical gates, as you can see on the table. That's an example of the just one very small window of the recording. We have a transfer function where input is directly funneled to output. We have AND NOT. We have conjunction. We have disjunction. And that's an example of the recording on all output electrodes. So what we found that distributions of logical gates to input one output logical gates recorded from this fungal colony is similar to distributions of logical gates recorded from slime mold, living slime mold, Flagellanum paracephalum, succulent plants, single molecule protein vertaxin, actin-bound infection. That probably indicates that fungal substrates or Mycelium bond composites can produce the same computational abilities as other living substrates do. Then later, we decided to check experimentally if it's possible to extract logical circuits from living fungal substrates. So Nick Roberts from our lab constructed this wonderful hardware and stimulated fungal substrates with 4-bit strings. That example of the output and table showing how, in fact, logical functions were extracted. And this is, you see, distribution of the logical functions. In the table, you can see top 16 highest occurring Boolean functions. Okay. Also, we can make computation in fungal substrates based on electrical analog circuits. It was demonstrated in our paper cited before. So we took 3D stacks of a single fungal colony. We converted it into the graph. We assigned to each edge of the graph capacitance and resistance. And then using splice modeling, we applied again inputs as binary strings, high and low voltage, and the calculated outputs on imitated output electron. We found that on serial network, we can implement select gate when input is funneled to output and AND NOT gate. On parallel networks, we can implement select or AND. So basically computation in fungal substrates already can be done in 2 manners, either using the spiking activity or using them as electrical analog circuits. If we go further and try to implement neuromorphic systems from with living fungi, we need to implement some learning or some synaptic weights. And here's memory resistance come in mind. Memory resistance is a resistance with memory. By applying current or voltage, we can change its resistance. And it's similar to the synaptic adjustment of the synaptic weight in artificial neurons. So to check if fungi can be used as synapses in neuromorphic structures, we checked their memory resistance and found that while not being pure memory resistance, because the spots don't show any pitch, living fungi show some infractals. So a mixture of memory resistance and capacitance. All the previous stuff shown to us that not only we can do arbitrary computation, implement arbitrary cascades of logical circuits. Not only we can do electrical analog computing with living fungal substrates, but we can also implement learning neuromorphic circuits. So in principle, we can make a brain, or at least simple brain, with living fungi. And now, at the end of the talk, I will discuss with you language of fungi. A year ago, I was curious if patterns of electrical activity of different fungi are the same. So I already had experiments on Ganoderma and oyster mushrooms. I also took Cordyceps militaris, commune mushrooms, and gloss mushroom at the bottom of this book. And insert electrodes and recorded for several weeks. But you can see example of the recording, where very nice train of spikes is shown in the insert, zoomed in the insert. So on the table we can see a number of spikes, analyzed, average interval in minutes between spikes and amplitude. Then I converted spikes into the binary images, where there is empty space if no spike, and a line if there is a spike, barcode representation. And analyzed distributions of the spikes. Here you can see distribution of a number of spikes in trains. Train of spikes is a group of spikes where distance between two spikes, which follow one another, is not more than double of the width of the spike. So you see distribution of trains of spikes for all 4 species of fungi studied. And on the right, you can see distribution of word lengths in English and Swedish. They are quite similar. Moreover, if you compare average length of a train of spike in 4 species of fungi studied and average word length in English, Russian, and Greek, you see comparison is striking. Train length in fungi changes from 3.3 to 4.7 highest in the details. And in languages analyzed here from 4.4 to 6. So like we can say, for example, based on analogy, Cordyceps militaris language is more common to Russian language. And for example, commune fungi speak more like in Greek. And then using Markov chains, we can reconstruct syntax of fungal language. It can be done by calculating probabilities of one spike, followed spike train, followed by another spike train. And then cutting off and leaving only edges or transitions with highest probabilities. And the graphs show to us syntax of a probable fungal language. And if we convert this human language to sounds, the fungi talking will sound like that.